Hi everyone. I actually will switch to English. I was asked by organizers to make this lecture in English, so it doesn't really matter for me to speak in Ukrainian or English, but this one probably would be better. So my name is Mykola Maksymenko. I'm director of R&D at SoftServe, and at SoftServe actually our team works in establishing scientific-based R&D. So we actually try to write our own researches. We try to push a little bit forward the frontier of what we are doing at the company. And this is one of the work that we've been doing for a while already with, in context of AutoML or general automatic hyperparameter optimization. So the idea of this talk will actually be that in some cases, you actually don't need now to fix on the set of hyperparameters. So you actually can learn and train your model in the way that actually in some combined space, you will get both hyperparameters and weights and end up with a good model. So here, I want to start from the very vague analogy. So imagine you drive a car in mountains. So this is a very complex landscape, right? And here, when you actually operate within the car, like you change the gears, you try to navigate within the road, this is kind of a training of the model itself. So when you change the weights of a model. But now imagine that the road itself is actually the set of hyperparameters that you work in. So this is something fixed. And sometimes, in some cases, particularly in this very complex landscape of mountains, this road actually cannot be straight. So you need to get here, right? But you see the road is actually very, very, very curved. So the idea is that actually it reproduces the landscape of this potential. Otherwise, if we fix set of parameters, we actually can go all the way straight, but not necessarily that we will actually get to the final point. Or we can try to draw this straight line to the final point, but then we'll get this like walls on our direction. So not necessary that we actually will be able to penetrate those. So the idea of this talk is actually will be to describe our recent paper, which we published last week, together with Maciek from ETH Zurich, Vlad and Jonathan from Technion. And here we actually will we describe the training of the neural network models in the combined space of hyperparameters and weights. And we will show that this allows us to actually efficiently sample hyperparameter space instead of selecting a particular set of hyperparameters. And it will allow us to discover so-called non-stationary scheduling. So apart from selecting a single point of parameters, we also sometimes do scheduling. For example, learning rate, when we actually drop it down over the course of training. Here we actually can discover much more complex scheduling protocols with this method. And we will show that we actually get better and faster training. And the idea of that is that if you try to go straight where we want to go, we actually might end up seeing some walls in this landscape. And this is very hard to penetrate. While when we actually go around, we actually might get much faster to where we want to go. So just to give you the quick outline, so I'm a physicist, so all that I'm doing very much inspired by physics. And particularly in this talk, you will see some analogies between machine learning and physics. So I use, in our work in R&D, we actually use some of the machine learning methods for chemistry and physics and basic science. And we also use physics as a formalism, toy models, and concept to actually attack machine learning problems. And you will see several of these nice analogies here. I hope you will enjoy those. And let's start from the very beginning. So currently we have really advancement of deep learning in all the spheres. We have self-driving cars. We can generate nice, realistically looking images. And all this is actually done by these very basic models, which have this layered structure, right? And they are trained actually also in very simple manner. So we have some cost function, which in this particular case is difference between true labels and predicted labels, and then we try to optimize this cost function by stochastic or non-stochastic gradient descent. And when we go to the global or semi-global minima of this function, we actually say that our model is trained, and it predicts proper labels for our data, right? It might be data like classification, but might be other models as well. And the idea why it works, generally, is that we have two theorems, which actually give us hope that this model should work. So one was Kolmogorov-Arnold theorem, which said that any complex function might be actually represented as a sum of single argument functions, and a universal approximation theory, which said that any complex function actually can be represented by a wide enough neural network. So that gave us a hope a while ago, and people were very much believing into these models, but it took another 40 years plus to actually get them into production. So when you go to statistical machine learning classes, the first thing you learn is that neural networks actually don't work because they require too much data and they overfit. And that was more or less the belief for quite a while. And only recently, when people actually started to explore deep enough architecture and started to get a lot of small tricks, it started to work. And if you watch carefully which are those tricks, so currently we see that a lot actually is dependent on the batch gradient. So instead of taking like large gradient, standard gradient descent, we take stochastic gradient descent, which is like sampling partly the data. And that's played an important role in training neural networks. So we need some stochasticity in the model. Another thing which was very much important was dropout. I see I have a mistake here. And some other methods were early stopping, and et cetera, et cetera. So, but generally, if you carefully look on those, a lot of these methods are somehow related to stochasticity. So somehow related to noise in the model. So, and I would like you to actually notice this, because this will be more or less as a main thing within this talk. So see hyperparameters as some kind of regularization or noise. And regularization can also be seen as kind of a noise in the model. And there is a common wisdom, and actually I want to test it here. So various type of noise or regularization actually allow us to avoid being trapped in bad minima. So just let's test it. So how many of you actually believe that if the model stops training or trains not very well, that we are stuck in the bad minima, in some local minima? So just raise your hands who believe in that. Okay, so I see, let's make this exercise again. So how much of you believe that it's not true? Okay, so we have majority, and that's actually good point. So let me describe this thing. So why do we believe that we are trapped in the bad minima? So this is a nice picture, right? So we have some short minima, and we have some flat minima. So generally, when we want generalization, we actually want to be trapped here. Because if we are trapped here, and over the training, let's say you are trained on this, this is your potential for training, but actual potential for testing is somewhat shifted. So imagine you actually train here, so your test error will be much higher than here. So this is just a very basic argument why this should work, right? And generally there is a paper, you can read carefully on that. It's a very good paper, why batch normalization works. But actually, it's not true. Not always true. So if you want to find the bad minima in the model, the likeliness of having these bad minimas in the model is almost zero. So it's very, very small. Imagine that you have highly dimensional system. So it's very improbable that in all the dimensions, you actually have a minima. So most likely you will have a situation like this. You will have some saddle point, and then actually the saddle point might be surrounded by some walls in other dimensions. So you kind of need to navigate within this path in your complex space along the saddle points, right? And so this is actually a very nice paper. It's from Joshua Bengio group, that graph. This graph is actually from Jan LeCun's group. So they kind of not collaborated, but went along with each other. So Jan LeCun's group actually looked on the distribution of the local minima, true minima in the model, and they just noticed that if you increase the number of parameters in your model, actually first it shifts towards 0 of the loss, and most of these local minimas are actually very close to the global one. And all you need to do is actually avoid the global one, because the global one is overfitting, so we need to be a little bit slightly higher, so we actually need local minima. And these will be more or less good on the general aspect among all those other global minima. So it's very unlikely that you have local minima in your model, and if you're trapped in those local minimas, these local minimas are actually good. So what the noise actually is for? So why it's the noise that actually helps us to train the models? So that's still the question. And the argument that we actually try to put, and we see it in our model, and in our we actually demonstrated also in our paper, and there are some other papers that we cite, is that the noise helps us to speed up the diffusion in this very complex space. So why diffusion? So generally, stochastic gradient equation, so it's this one, if you write it in continuous form, it's actually a diffusion equation. It's a Langevin equation in math. So, and when we talk about diffusion, this is basically a distance that the particle in this very highly dimensional space travels over some time. And why the noise helps? So the noise actually renormalizes the potential in the way that it becomes more smooth. So if you have some complex potential like this, without noise, the particle, this is your network, which you want to train, actually moves very slowly within this potential. So it sometimes bounces the walls and bounces back and so on. So you cannot actually penetrate the walls that easily. But if you add noise or other regularization, you actually smoothen this potential. So some of the walls actually become smaller, so your particle or your network actually moves faster and trains faster. And so on and so forth, and actually discovers some good local minima, finally. And we tested that, and we see it in terms of dropout, for example. So this is, I think it's LeNet network, trained on CFAR. And we have different levels of dropout here. So when we start to increase dropout, we see that diffusion actually increases, so it becomes faster. So diffusion is distance between initialized network and basically Euclidean distance between vector of initialized network and vector of network at some point in time. And we see that actually when we have more dropout in the system, the particle or our network actually travels much faster. And this is important for training. So if you look on other hyperparameters, it's not all the hyperparameters that have this property, but a lot of them. And here in this example, I show you that dropout actually has this property, learning rate has this property, and any others which actually involve some kind of noise or stochasticity actually have this property. Also, changing the batch size also has this property. However, for example, L2 regularization does not fit here. For L2 regularization, because we constrain the value of values in our weights vector, we actually at some point start to suppress this. So it does not really work there. But for some other hyperparameters, it works. So this is very important message. I hope you enjoyed it. But now we will move to actual hardcore part of this talk. So I wanted to talk about how to optimize neural networks in the joint space of weights and hyperparameters. And We do this currently without joining spaces in a either very naive way or in slightly less naive way. So naive sequential search is such that you start with some model. And here I have a model which is this white things. And the border of this square color of the border basically represents the parameters. So you have hyperparameters. So you start with some model, you train it over the time, and then you discover that actually the actual performance of the model is very bad. So then you start again with some other hyperparameters, different color. You train again, you get a little bit better performance. Well, you might have some guess which parameters you should choose next time. So you could use some kind of Bayesian search for hyperparameters. So you choose the last one, and actually you get the good performance. But all this sequence actually takes a long time. And another thing, it still limits you to a set of hyperparameters. So now, oops, what happened? The second approach is a little bit more smart, so you can parallelize this very easily. So you start with many guesses of your hyperparameter. This could be random grid, this could be some smart grid, or this could be some kind of, again, Bayesian approach. So, but at the end, you train a lot of these models, you train them in parallel, you get some good result, you go with it. So this is a standard way. And again, you limit it to a set of parameters. So what we want to showcase here, and what already was tried by another group as well, so is merging hyperparameters and weight space. And here is an example where it was done in slightly different manner than us, and actually it's kind of a subclass of our model. And this is a greedy approach. So let's say that you have, again, parallel set of your networks. You train these models, and at some points in time, you actually compare them. If this model trains worse than this one, you actually exchange, or this one trains worse, you actually take the hyperparameters from this one, move them here, slightly perturb, and go on with that. So in this case, you actually kind of exploit the fact that this model trains better and explore a little bit around that vector. So the idea, if you look on this, how it looks in this hyperparameter space, is that you have multiple starts of your models, but then you actually converge to some dominant tree of the hyperparameters. So this is actually a paper by DeepMind, and this is a method that they use in production a lot. So they showcase that on a range of models, for example, StarCraft, Atari, then on machine translation and guns, and they showcase that in all of these examples, it actually is much more powerful than the standard parallel grid search. But still, there is a problem. And as I showcased, this is a greedy approach. So it's still very much dependent on the initial conditions that we started. So if we actually, and there is no guarantee that actually it will explore this space correctly, because we always exploit it. So we don't, the exploration part is very uncontrolled here. So they also claim that in their paper that unfortunately they cannot guarantee that it always works. So what is our approach? Our approach is slightly, in some case, similar, but slightly more forward thinking in terms that we don't work in the greedy manner. We actually are guaranteed that we explore all the hyperparameter space correctly. And the idea here is, what if different models here will be examples of being a different smoothing potentials. So in this case is, in terms of physics, these are different temperature. So this temperature is the lowest temperature, this is the highest temperature, like the potential is very smooth. And in this respect, we actually allowed models to go on with training, and then we change only hyperparameters, at some point of time, allowing actually well-trained models sometimes actually move back to another branch of training. So in this sense, we actually do so-called parallel tempering method, which goes from statistical physics, and is guaranteed to actually explore the space in the proper way. So if you train this model long enough, we always actually will explore it correctly. So in practice, it looks like that. So we have multiple GPUs. We start with some hyperparameters, and then on the way of learning, we actually sometimes exchange their paths. And this path exchanging is basically exchanging only the parameters values. So it's very quick operation. It almost gives no overcost for our training. And it's very easy to implement, actually, once you have this parallel training. So in algorithmic form, it looks like this. So it's more hardcore slide here. But you should focus only on these two parts. So here we say that we actually perform standard gradient descent for each copy. And here we say what is the rule for actually swapping the hyperparameters. So every number of epochs, we actually say that we measure the average loss of these networks. And if the loss is of one network, which should be on the higher temperature is higher, we actually exchange it. Or we exchange it with some probability, which is Boltzmann probability, which comes from statistical physics. So you can actually find more details in the paper. I don't want to overdose you with formulas here because it's last talk, so it's hard to follow. But let me give you some good examples that we did. So the first experiments that we ran, I actually ran it quite a while ago, were actually on MNIST. And then we ran them on eMNIST, this a little bit more advanced data set, and CIFAR-10. So these were LeNet kind of networks, and we've seen already that if we start working with these exchange networks, which are blue lines here, exchange models, so they actually outperform random grid search. And another set of experiments was actually on the ResNet networks, on ResNet 22 and ResNet 20 and ResNet 44, where we actually, again, implemented that on CIFAR and compared that with a standard benchmark on ResNet networks. And we've seen that, again, we win few percent of accuracy here, of error, and we always see that this is lower values than actually in the benchmark. And moreover, as you see here, this is a nice plot here. You can see that we, along with this training, we can now reproduce it by just following how we change the hyperparameters along training. So every couple of epochs, we can actually change the hyperparameter along this line and reproduce these results. So this is more or less all that I wanted to highlight here. So once again, we introduce different manner of training deep architecture now in the joint weight and hyperparameter space. And we see that we discover actually the protocols, the optimal non-stationary protocols for changing hyperparameters. And we see that this is more efficient than actually standard grid search, or even it's actually more broader umbrella for other methods which actually are more greedy-like methods. So if you want to actually turn this method to greedy, you, instead of taking probability of exchange, you just always exchange. So this is more general method. So that's all from my side. I will be very glad to hear your questions. Thank you.
Спасибо. Спасибо большое. У нас есть один вопрос из чат-бота на экране.
You can use reinforcement learning, but why? I mean, it's slightly different set of questions. Yep. I think I would be easy actually to talk like this.
Hi, it's very interesting. Your presentation is very interesting. I wanted to ask a question. each time brings good results, while using Adam creates just trash. Example is propagating through trained guns to create a good image. And I have a question. In very simply talking, you have optimizers. As I understand, you have optimizers and weights. You compute different gradients. So these different optimization rules choose the best model and take the best optimizer or average of some best optimizers and average of best gradients. Do you understand? In very simple.
You mean in this simple
yes,
way?
in a very simplified way. Yes.
Right.
Does the method lead to the very aggressive overfitting like Adam in 10th degree? Because sometimes we need to wait for some time, for example, when we use SGD to find the good local minimum. Are we just searching for the most shallow minimum with this approach of temperature?
Sorry, I'm a bit lost because you jumped from one question to another. Like,
no, this is
yeah. So you started about yes.
Finds a better minimum sometimes.
Okay.
And this approach seems for me like finding the most shallow minimum. Because
SGD also looks for the shallow minimas. So it actually because you sample your data set in this stochastic manner, it actually can we get back to the slides? Okay, never mind. So it actually kicks your network outside of these very narrow minimas. It's not only in GD, it's actually any stochastic gradient descent like methods.
I just wanted to express the concern. Maybe we have in some situations even worse as an Adam optimizer, because we're just searching for some very shallow minima, trying to move as fast as we can. Without waiting for some time, because if we wait, for example, a couple of epochs, we find that model evolved into some much better state.
Let me think. Let's talk about this probably after. I need to think a little bit about that, but
Еще вопрос?
yeah.
Скільки моделей ви тренували в паралель, щоб обмінювати вагами?
So okay. Shall I switch to English or let me just answer in English. So how many models did we train here? It was, I think, 8. It's again, slides are gone. Yes, so we have here 1, 2, 3, 4, 5, 6, 8 models.
І наскільки швидше вдавалося знайти, ніж байсовським пошуком гіперпараметрів таку оптимальну конфігурацію?
We did not compare it to any bias or anything like that because it does not make sense to compare it to those. It's a completely different method. So it's necessarily faster. So it actually, like, you can see it even on these plots or on these plots. So you can actually achieve lower results much faster than, let's say, standard grid search. Okay, in the bias method, you probably will go lower, but still it will not be comparable to this.
Це більше питання про практику, чи от, якщо в мене є задача...
That's engineering question, like, come on. You can also over-engineer this method to go much further. So it's theoretically more advanced. Yeah.
Спасибо. Есть ли еще вопросы? Вижу.
Thank you for your talk.
Thanks.
Very good method. Can you please say, do you have any extension? So you need a lot of runs in parallel, and during runs you make the swaps.
Mm-hmm.
Can we use this information you already received with this 8 training in some second step? Run 8 more and use some hyperparameter information from this run, like step by step.
Like if you have too many hyperparameters, generally it works to it generalizes to many hyperparameters, not only single.
Not many hyperparameters.
But
I mean, you found some interesting
path?
scheduling
Yes.
of learning rate, and can you not start?
Can you take this best model that
best
you get?
model and some maybe differences and swap between them and find even better path, something like this. So
You mean from scratch?
not from scratch, stretch, take some information of scheduling from this as
Okay.
useful information,
Right.
and restart again in parallel 8 more.
Well, in principle, what you can do. So, for example, you have set of hyperparameters. You discover this path for this set of hyperparameters, and then you have some other set of hyperparameters. So you can kind of disconnect them. Maybe you can think about this in this way. But what we would recommend is actually to combine this in a one run. So such that you literally search for this, going around, you know, all the walls and like avoid them.
Why I ask this question? Because when you work with C410,
Yep.
okay, you can run 20 parallel.
Yep.
But when you train on real data set, you are lucky if you can do 4. Okay.
Yeah, but
How to
it
extend
depends. Yeah, it's a good question. I think generally we did not currently move to like engineering version of this, going into production, but this is what actually DeepMind tried on their version of algorithm, which is kind of similar, I would say, in this like when you go to production. So, and they actually went to really large examples. So I would say here is StarCraft or some machine translation tasks. So it works well. And you can actually combine two cases. Let's say our algorithm works well when you have this noise-like hyperparameters, while for those which don't work as noise, you can still use this. So you can actually do that in the same run.
I have a question.
Yep.
Why do we actually swap the parameters rather than just resample it in random interval times? So is it necessary to swap them, or we can do any other scheduling scheme like in random time intervals? Like for example, you just randomly resample the weight. Or
Yeah, so that's very important. That actually, particularly this swapping, so this is Metropolis step. So this is very important to actually keep the detailed balance in your model and actually sample the space correctly. Otherwise, you actually will go either in greedy way or in random search. So otherwise, you actually are not guaranteed that you sample the space correctly.
This has some theoretical background.
Yes.
Okay.
So this is very important part. So what is actually makes difference here?
I will definitely learn your paper. It's very interesting. But as for now, a very naive question. Do we become a witness of historical breakthroughs now? For example, like imagine if we here talk about dropout, and then after we see the dropout in the back of tricks for machine learning engineers. So something new is wow effect. Then everybody adapt this technology, and it's like must have. Do we see this in, how do you think? Do we see this the same with your theory? Will it be really with impact in practice?
I hope so.
And so in which bucket we can take your technology? Is this something special, or is this really like drop out and everybody uses it?
It actually, yeah, it's like dropout. It's actually very simple to implement. So currently it's more like our code is more research code. It's probably a little bit over-engineered, but generally it's very simple to implement on top of some existing methods.
So I hope that it will be.
Yeah,
really
so we actually, currently a plan is for next iteration of this research to make it more, to democratize it and
so
actually it's
okay,
open
because
source.
my main question was I will take a photo with you, and I will have photo with famous guy. It's cool.
Есть ли еще вопросы?
As far as I understand, you did random swap, but was you thinking about something more not random but clever swap?
Excuse me, can you repeat the which?
I thinking about something more clever swap, selecting two models that have. best
I-
results and swap from that.
No.
model or something?
So that actually was that other approach. So
Mhm.
they just took like the best model and actually go with those parameters. In our case, we have this more clever trick,
Mhm.
which actually allows to sample space correctly and explore it much in guaranteed way. And this is a standard. So I don't have these formulas here in this presentation, but you can walk through our paper.
Mhm.
So this is a Metropolis step which allows us, so we make a swap if we see that we actually gain advantage, but we actually exchange the temperature, so that other replica still trains.
Mhm.
And we still can make the swap with some probability.
Mhm.
If we see that it's probably not optimal, but there is still some probability that we make a swap.
Okay, so the other question is, if you swap, so you continue training both model, and in some period of time you can swap again between that two models and
Yes.
return the original.
Yep.
Mhm.
Which might be not optimal for that moment in time, but will be optimal in global sense.
Okay, clear, thank you.
Есть ли еще вопросы? Нет. Спасибо большое.
Yeah, thank you.